Sound seems a little better now, so let's hope you can hear everything properly. So, is the existence of a cross-equatorial pressure gradient sufficient condition for inertial instability? Again, I won't go through the details of the calculation, but just show that it's not sufficient. If you have static stability on the other side, then convection inertial instability is not going to be very good at setting up convection. Okay, so look at a simple schematic of a zonally symmetric shallow fluid model used to represent the tropical boundary layer. So it has a average height of h beta, which is shown here, and there is a jump of delta theta across the boundary layer, which has got this tilt. So there is h1 greater than 0 above the average height and h2 less than 0. You have theta 1 on this side and theta 2 on this side because of this jump, and you have a pressure gradient, pressure T1 and pressure T2 set up here, which gives us the cross-equatorial pressure gradient. We are looking at cold to warm meridional direction here. Okay, so the temperature difference is going to drive the pressure gradient. We can write our governing equations again about background state, basic state u bar y as we did before. So du dt plus nu uy minus beta y plus alpha u, like a friction term, which is approximately similar to the dissipation term used here for this idealized situation. In the meridional direction, we get this equation for perturbation flows, and we have the vertical equation in terms of the geopotential height variation. Here CB squared is G tilde HB, where HB is our average mean depth of the boundary layer. G tilde is our G delta theta over theta, which is like our reduced gravity that we did before, right? So set U bar equals gamma C times Y, where we are relating the horizontal meridional sheared balanced winds, basic state, to the vertical stability. So using equation 1313 actually, and solving for V through the elimination and U and phi in this equation, in these equations, all kinds of wrong numbering, Peter. We obtain this equation. Again, we are obviously going for wave form equations, so we can see whether instabilities do exist based on what conditions. Write v yt as meridional function times exponential I omega t. So you're going to look for imaginary frequencies. So y prime is written as y minus gamma c over 2b, and omega prime squared is omega minus I alpha plus gamma c squared. So we have obviously skipped all the steps and directly jumped to solutions. V here is written as beta over cb to the 1/2, which gives us the equation we want to solve, d squared v dt squared actually, minus plus omega prime squared over beta cb minus v squared times v is 0. This is similar to the equation 511 we had seen before, and the process we used to derive the harmonic oscillator equation out of that in chapter 6. So that's the same process used here, and you can see the similarity of the two equations except for the more complicated dispersion relation here. Okay, so omega squared is beta cb, which is equal to omega minus I alpha squared plus gamma c squared over 4, or omega squared is beta cb minus gamma c squared over 4. So for omega to be imaginary, to get instability, gamma c squared has to be greater than beta cb. Again, I'm skipping a lot of steps and just getting to the point we want to make about the physics, because if you are interested in these sorts of details, you'll have to go through not only the book but the numerous papers, mostly Peter's papers, that are cited, so that you understand the processes. So this equation basically suggests the relation between inertial instability occurring only if shear of the horizontal wind is sufficiently large to overcome the impact of static stability. That's the main point we wanted to make. You can have a strong cross-equatorial pressure gradient, but when you cross the equator because of this pressure gradient, if there is a very strong static stability on the other side, then inertial instability will not occur. This is the main point we want to make. So that's why I skipped the equations a little bit, but you can go and do that. This is an example. So we're looking here at the vertical profiles from way back, averaged over 1981 to 2000. So the red line is the observed values, and the this is for the Pacific, just south of the equator in the eastern Pacific. It is in the heart of the cold tongue, and this is north near the ITCZ, 95 west, so it's in October, so it's basically in the ITCZ. And here observations are compared with ERA 40 just to give you a sense of it. So you can see that at 2 south 95 west, which is in the southern hemisphere, there is a jump at the top of the boundary layer, which makes it hard to create instabilities, and the same in the equivalent potential temperature. But across the equator on the other side, you can see that there is the potential temperature is doesn't have the strong jump, but it has a structure that is obviously stable to dry convection, increases with height. But if you look at equivalent potential temperature, it has a negative gradient, which is conditionally unstable. So in this case, any meridional shear is going to create inertial instability. Okay, that's the main point. So vertical profiles of potential temperature and equivalent potential temperature in the Indian Ocean, on the other hand, do not have this ability to drive inertial instability. So even if cross-equatorial pressure gradient is strong, thetas at both 60 east and 80 east, this is on the Arabian Sea sector, this is on the Bay of Bengal sector, in October, do not have, so the atmosphere is basically stable, and to drive across this static stability, you will need a shear that's something like 50 meter per second, I think. So that's the number that you can look up in the book, but basically we are still making the same point, that in the Indian Ocean you don't have inertial instability because the static stability is too strong. South of the equator also you don't have inertial instability, but north of the equator in the eastern Pacific you have conditionally unstable situations, so cross-equatorial pressure gradient is going to drive inertial instability. Okay, so please read up if you are more deeply interested in that. I'm kind of keeping it brief and descriptive because the main processes are given in such detail, but it is all diagnostic. Okay, that's kind of what my point would be.